How's it going, everybody? In this video, we're going to go ahead and take a look at our next topic, which is going to be EIGRP path selection. This is going to take us a little bit to work through, but as we get into the meat and taters of it, I'll break down everything, and there's going to be a lot of whiteboarding. It's going to be mostly theory. So I'm going to go ahead and get out of the way, and we're going to start talking. So there's actually quite a few things that we need to take into consideration when we're talking about how EIGRP figures out point A to point B operations. So there's a few things that we need to take a look at in terms of how that's figured out. So we have the composite metric. So that's the first thing that we need to talk about. What is the composite metric? The composite metric is always going to be the lowest, right? The lowest metric. Let me clear up some of my handwriting here. It's actually pretty atrocious. One of these days I'll get TRIC in there. So the attributes that are used in order to determine the composite metric are going to be bandwidth, delay, load, and reliability. Now, each one of these has a unique set of characteristics. So the bandwidth is going to be the lowest bandwidth along the path in kilobits per second from point A to point B. In other words, what is the lowest, or the slowest link between two endpoints, source and destination? Whatever that link speed is going to be what we need to use as our calculation variable for any traffic that goes along that particular path. What do I mean by that? So if I have a scenario where I've got R1, R2, R3, and then R4. Okay, I have a couple of different ways of getting there. Trying to keep the topology somewhat small so that it's easy for you guys to follow. So if I have a scenario where, let's say all of these are 1 gig links. So I'm just going to put a 1 for simplicity. This is a 10 meg link, and this is 1 gig. So meg, gig, 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 and gig, respectively. What is going to be the shortest path between R1 and R4? So R4's got a LAN segment sitting behind it. R1's got a LAN segment sitting behind it. And then R2 and R3 are going to be basically just transit links or transit nodes between two different destination networks. Well, we're going to take this path and this path equally, right? Because we have 1 gig across the board. Now, what happens if something happens to, say, this link right here? Well, we're only going to be able to take this path right here, right? We'll take this path around. But what happens if this link is working fine, but this link goes down? Well, we can take this path, right? So you're like, okay, where does the 10 meg link come into play? Well, there's technically an alternative path right here. So if this link goes down, this link is dead, we could send traffic this way as well. Now, if this link right here goes down, let me back this up just a little bit. If this link goes down and this link goes down, let's see, I want this one. I only have one other choice, which is to go this way. Now, these are 1 gig links, and this right here is 10 meg. So, what is going to be our bandwidth that we're going to be using for our calculation? It's no longer going to be 1 gig, right? It's going to have to be 10 megabits per second. That's a significant drop in bandwidth from the 1 gig links that we've been using. So EIGRP is going to take that into consideration and go, okay, if it's a lower speed link through the amount of kilobits that have been assigned to that particular interface of the EIGRP process, that means that the bandwidth is going to have a much higher value. So it's going to adversely affect how EIGRP is going to calculate the route. Now, that's how the bandwidth piece comes into play. Now, if we were to take this back to where we're at here, the next one we have is delay. Now, delay is the cumulative delay along the path in tens of microseconds scaled by 256. Now, delay is calculated in tens of microseconds. So we're tens of microseconds. We'll put ms here for microseconds. Technically, this is milliseconds. Microseconds is actually US, in case you didn't know that. And for every 1 microsecond, or 1 in this particular part of the output, equals 10 microseconds. You just, right there. Now, US. Now, if I have 10, this is going to equal 100 microseconds, so on and so forth. The load is going to be the highest load along a path. So what that means is and these two right here are off out of the gate by default. These are not used for metric calculation. Their K values are actually disabled in EIGRP. They can be turned on. I don't recommend you doing that. When we do something like this, and we're looking at bandwidth and delay, remember we're looking at this in increments of 10 microseconds, and it's a cumulative delay. So if this is 25, this is 22, this is 300, this is 61, and this is 27, we have some math to do, right? This path right here would be how much? 25 and 27 is what? This would be 52, 22 and 61 are, that would be 83. So this will be 83. Then this path right here, 300, we'll just tack on plus 300 here and plus 300 here, right? So 352 or 383, depending on which way you go. So basically that's how that would come into play. Now, when we talk about this in terms of load and reliability, we have to take into consideration that load is going to be utilization. Okay, utilization goes up, load is going up. Reliability is going to be in how trustworthy is that link. So if it flaps a lot or causes us problems, it's going to have a lower reliability. Both of these are scaled in increments of 1 through 255. So if you loading, you're always going to see someone like myself or another instructor. Most of the time, you're going to see this one get a value of 1, so the lowest loading option you can get, and this one's going to be set to 255 to be the highest reliability on a per link. This is more specifically to redistribution, when we had to redistribute something into EIGRP, like another routing protocol, a connected route, a static route, so on and so forth. So with those understood, we have to take that into consideration. These 4 attributes are looked at on a per physical link basis. Now, let me clarify that just a little bit with you. When I say R1 and I say R2, and there's a physical link between them, in our topology, everything is a physical link. But if I have R2 and I have R3 that are physically wired into the same switch, and they're both placed into VLAN 23, and this is on this interface right here and this interface right here, we are using, let's say, gig 1, and then we give it a sub-interface of 23, and we set the encapsulation to be .1Q23, so to pay attention to anything tagged with VLAN 23, then this is still going to be a physical link, but it'll be a VLAN tagged link. Still physical, just logically separated inside the switch. Just keep that in mind. Okay, the next thing we need to understand is going to be the metric calculation. So how does this get worked? So the composite metric is computed. It has to be. We have to figure out how to get everything in place and working. I'm going to go ahead and clear the screen off and start up another series of topics that we need to go through. The route with the lowest metric is known as the successor. The successor is going to be your winner. This route goes into the routing table. So actually used by the router to get traffic from point A to point B. Any other routes that are less preferred or have a higher composite metric, but still potentially could be used in a reconvergence or a network outage type of scenario is known as the feasible successor. And what I mean by that is a really good example would be president and vice president. So the president is the successor. They are in charge of the country, right? If something happens to the president, then the vice president takes over. So he is the feasible successor. Simple hierarchy in that respect. Nothing more to it than that. I don't want to get not political in any respect. Just it's a position and how they are handled. Now, the feasible successor comes into play, and I like to refer to this as the second winner. And this guy right here is only injected into the topology table. And we'll talk about the tables here in a little bit more detail and how they come into play. So that's basically how they are broken down and explained. Now, whenever a route is determined in the network, the successor's metric right here, we have a couple of other terms that we have to add in. The first one is going to be the feasible distance. And the idea with the feasible distance is this is going to be also known as the composite metric, or the end-to-end metric that's used to get for traffic from A to D in this example, or maybe a better analogy would be source to destination, something along those lines. Now, there are metric weightings that come into play to help figure all this out, because remember, your metrics, your bandwidth, your delay, your load, your reliability, etc., they're what they refer to as K values. The K values themselves are turned on and off. So if you have a off would equal 0 and on would equal 1. At least the metric turned on with the value of 1 and the K values underneath the EIGRP command of metric weights, and then you turn a particular K value on when it's normally off. By turning it to a 1, you're effectively turning it on, but giving it the lowest, lowest priority, or lowest, actually precedence would probably be a better way of referring to it. Lowest precedence. Now, if you were to take this number right here and jack this up to something higher, like 2 through 256, the larger the number, the higher the precedence. Let me clean up my penmanship here real quick. That's how that comes into play. Now, you can modify these across the board, so you can have like 1, 2, 73, 88, 125, stuff like that. You can go get creative with them and play around with them. When you do this, you need to make sure that all routers match. The idea behind this is actually very, very simple. If you have a scenario where you have a number of routers that you're running EIGRP and you feel like you need to play with the metric weightings underneath the EIGRP process to mess with that for whatever reason, good, bad, right, wrong, or indifferent. I may not agree. You might think it's the best thing since sliced bread. That's your call. If you adjust those metric weights for whatever reason other than the defaults, you need to make sure that you adjust them on every other router in the EIGRP domain. If you do not, the neighbor adjacencies will come down, and then you will also have inconsistencies in your final composite metric. EIGRP has a kind of a self-protection mechanism in place where if you do modify the metric values, you'll automatically have to adjust them everywhere else because the adjacencies will be torn down. That's even more of a problem than the EIGRP calculation coming up to be different, because, for example, if you and I are both into the same thing, whatever that might be, and we're getting our information from different sources, I might come up with some understanding of whatever that is, and your understanding might be different. If our understandings don't line up, then we're not going to be able to figure out what the best way to get traffic from one place in the network to another. So as long as everything is across the board even, and everybody has the same understanding of how to interpret the details that we're receiving from everybody else, then we have a much greater likelihood of coming to the same final answer with everything, and then we're all going to be in agreement on how we should move traffic throughout the network. The idea is to not complicate things that don't need to be complicated. It's all about trying to keep everything very, very simple, because if you add complications to things, that's when problems occur and stuff breaks. So with that being said, if you modify the metric weights, keep that in on the back of your head, that if you do modify that, that's a potential problem. So let's talk a little bit more about how the operations come into play in terms of the day-to-day stuff. Let me go ahead and clear the screen, and we'll talk a little bit more about the terms. So we have the successor, which is going to be your best path. You have I'm going to put the feasible successor is going to be a composite metric of the best path. In other words, a backup path. The next one we have is going to be the feasible distance. This is going to be the composite metric of the best path. We have the advertised distance. I'm going to put ADV, advertised distance. The advertised distance is the composite metric learned by the neighbor. So what we are told about. So this is going to be the composite metric from neighbor. The next one we have is going to be the local distance. This is going to be the composite metric to reach our local neighbor. So composite metric to neighbor. A couple of little things to pay attention to here. The advertised distance is also commonly referred to as the reported distance. If you use advertised distance, that's acceptable as well. But reported distance is also something that I've heard people refer to, but most people use the term advertised distance. The feasibility condition comes into term, and the feasibility condition is basically a criteria for a valid backup path. So backup, let me just put BU path criteria. Now, when you come into a situation like this where you potentially have more than one way to get from point A to point B, and you are trying to figure out which way is the best, you have to have some way of doing that. That's what the feasibility condition is. Now, the feasibility metric, the way that the feasible condition comes into play, what that basically means is if I am going from point A to point B, I have more than one way of getting from point A to point B. Any of those other options, option 2, option 3, option 4, you need to have some sort of way of examining those backup routes. In the event that you need to, you're already have gone through and pre-calculated those routes to make sure that they're not going to cause a loop and you're going to be in good shape. So the feasibility condition is going to find the best path. So best path first, right? Best path is first, and then backup paths second. Now, the way that it does this is if the advertised, that's supposed to be an A, advertised distance is less than your feasible distance, your path is good, meaning that you're loop free, and you're a viable backup. In other words, if your metric is lower than mine, you are closer to the destination and loop free. So remember, feasible distance in end to end, so let's do this, feasible distance equals the local distance and the advertised distance combined. So you take these two together and you end up getting the feasible distance, or your composite metric. Remember that the advertised distance is everything advertised to me. So for example, if I am R1 and I have R2 and I have R3, I have R4 and I have R5. I have a very simple network topology. So from R1 to R2, this would be my local distance. Local distance here, local distance here, local distance, let me break that L up just a little bit. Local distance here, local distance here. In other words, anything that's physically wired to me. Now, if I am R1 and I want to get to R5's LAN segment, how many different ways do I have to get there? Well, I have this way here, right? And I have this way here. Which way is shorter? Obviously, R1 to R2 to R4, right? So this one here, actually, let me do this one. Let me write it this way. Let me change my color just to be a little bit. I have yellow, green. I have this path right here. And then I have in, let's say, light brown, I have this path, right? Which path is more preferred? Obviously, my yellow-green path is going to be, this will be your feasible distance or your successor route because it's the shortest path. It's got less physical hops to go through. Now, that's just based off of what we're looking at, but from a hop perspective. But if remember, EIGRP doesn't look at it from the perspective of how many hops away, but what are the link-specific metrics: bandwidth, delay, load, reliability. So for the sake of argument, we're going to say that the green path is the feasible distance, and that the light brown path is going to be our potential backup route, right? So this might be a feasible successor or a backup. Now, the way that this is going to come into play is when I look at the operations of how things are working. If I am R1 and I need to get to R2, I'm going to have two different ways to go, this way or this way. Let's assume that everything is in a good position and we're going to choose the R1 to R2 to R4 path. So R1 to R2 to R4 to R5. That is the feasible distance or successor route. R1 to R2 to R3 to R4 to R5 is going to be our feasible successor or our backup route. Now, remember that R1 is going to go to R2 and use the local distance to get there. R2 is going to look at R3 and R4 and R5. R2 is going to know that in order to reach R5, it'll have to have some sort of metric value, and that information will be the advertised distance. The advertised distance is how R2 will go this way or how R2 will go this way. Now, the path, if everything is the same across the board, R2 should take the path through R4 to go to R5 because it's simply going to have a lower metric value. When you have a situation like that, as long as your advertised distance here is lower than my feasible distance here, I am going to be able to have a backup route. So which route am I going to take? My feasible is R3 going to be a viable backup route? It will be in this particular case because the advertised distance to go via R3 to R4 versus R2 to R4, R2 to R4 is going to be a lower value. So the advertised distance between those two endpoints, or to reach R5, is going to be a lower value. So if I go R2 to R3 to R4, that's valid. because the advertised distance is going to be lower than my feasible distance, because remember that R1 is looking at that particular path through the eyes of what R2 is telling it. So, for example, if R1 is telling if R2 is telling R1 that this path right here from R2 to R4 to R5 is a value of, let me come back in here and adjust this. This is 100, and then this one here is R2, the advertised distance. Right here, the advertised distance is 100 for this one, and the advertised distance here is a 125 for the advertised distance going this path. But on the total connectivity here, we have R1 is seeing the feasible distance on this route. The feasible distance here is 150, and the feasible distance here, let me bring this over just a little further. The feasible distance on the longer path is 200. Then, because the feasible distance is bigger than my advertised distance, then I'm going to be good to go. So at the end of the day, as long as the numbers work out, you'll always have a backup route as long as you have an alternative path where as long as the advertised distance is lower than the current feasible distance, you have a valid backup route. And that's where that comes into play. So just keep those things in mind in terms of the operations and how things come into play as you're going along. So that is basically how that all works out. Now, there are some other details that you need to understand in terms of the operations and stuff like that. I'm not going to get super deep into the actual specifics, because honestly, if you do get questioned on that, it's not terribly difficult to read up on some of the more advanced EIGRP options. There are some out there, but the basics to it is when you are looking at EIGRP in total, I personally have never seen anybody, I was never asked on any written exam that I've ever taken to choose the correct EIGRP metric calculation. No, I've never been asked a question like that. So I'm not going to walk you through how to manually calculate the actual composite metric. Just be aware of what it is and how EIGRP figures out the routes from point A to point B. As long as you understand advertised distance and local distance and you're able to decipher what they are, which we've already sort of taken a look at that. We'll dive into in a little bit more detail. As a matter of fact, since I have an active network, I'm going to go ahead and show you what that looks like right now, just so you guys can see how it comes together. But there's a lot of theory and a lot of specific understanding that you need to have in order for a lot of this stuff to be well understood and well executed on. So let's go ahead and I'm going to clear the screen, and we're going to go up, and I have to make a couple of quick adjustments to our topology because the authentication failed. I can actually adjust the keychain on both. So for those of you that are potentially studying for the CCIE, you can't remove a configuration, but you can modify it. So if we were to do a show run keychain, we're going to show run section keychain. We're going to adjust the send and receive lifetime of key 2. I'm going to go ahead and say keychain SHA, and then key 2, I'll say that the last portion here will be infinite, and the last part for send will be infinite as well. We'll just say infinite. Just like that. So we'll do show history. Oh, it won't let me do that. Well, that's not cool. So we're going to do a show run section key. We'll adjust this one as well so we can get the adjacency back up and running. Go to global config. We'll go under keychain SHA. Underneath key 2, we'll adjust this guy to be infinite. And then the send lifetime will also be infinite. Just like that. So now our connection's back up. If we do a show IP EIGRP neighbors, I'll have an adjacency to router 4, my connection to 6 is down because of the fact that the authentication for that particular interface is not set up right. So show run interface gig 0/1, we'll go ahead and quickly adjust that. So on 6, if we show run interface gig 0/1, we'll see that we can adjust that really quickly. We're gonna show keychain. I should be able to run that command on 5. So we'll go to, actually I'll remove the keychain on this guy. Let me just remove that command real quick. Now we'll type in IP authentication for mode will be, oh no, I have to have the keychain, never mind. Let me throw that back in there. Throw that back in there, and then do show run section key. I can toss that back in real quick on here. Grab that guy right there. Go over to router 5. Do show key chain. We have the keys there, and then we'll type in interface gig 0/1 IP authentication EIGRP, or mode will be EIGRP 100 MD5, and then, oh that's right, it's named mode. Router EIGRP named mode, and then we'll type in address family IPv4 autonomous system 100. AF interface is going to be gig 0/1, and then we'll type in authentication. Keychain will be, I believe it was being used, EIGRP, and that should be all I need to do. The mode will be MD5. That should bring that adjacency up. There it goes. So you can, it's backwards compatible, as you can see. So do show IP EIGRP interface detail gig 0/1. We can see that we are now using MD5 with the keychain of EIGRP, and we're in good shape. So now that we have that done, we're going to do a show IP route, and we're going to have a bunch of EIGRP routes in our network. If I look at just the EIGRP table, we'll see what's going on here. So one of the things that I want to point out to you real quick, if we were to do a show IP EIGRP topology, we're going to have a lot of routes. And if you look at how the routes are broken down, you see this FD right here. This means feasible distance. This value of 3276800, this is our feasible distance on the left, and our local distance, so our cost to whoever our neighbor is, that is their cost. That's what they're advertising to us. So this is our advertised distance, this is our feasible distance, or I'm sorry, our local distance combined together. I'm sorry, no, take that back. This is our feasible distance end to end. This is our distance to our neighbor. So if I was to take those two numbers and subtract them, you would come up with some value, and that's what the neighbor adjacency would be. So if we do a show IP EIGRP neighbors, and we look at the detail for gig 0/1, for example, we're going to see that the configuration is not going to give me the output that I'm looking for. EIGRP interfaces detail gig 0/1. We are going to see that, well, it doesn't tell me what the metric is, but it really doesn't make much of a difference. The idea is that when we look at the topology table, and we see these outputs, and if we were to grab a specific prefix like 10/128 here, and then look at the outputs, whoops, I meant to say /24, we'll see that the left hand side here, this is going to be at the feasible distance, which we can see right here. The feasible distance is 3276800. That's what this is. The one to the right here, this 262,144, this is going to be the local distance. So what my or the advertised distance. The distance between me and whoever I'm connected to will be the difference between these two. So if I was to take a calculator, pull this bad boy up, and let's do some simple math here. We'll copy that, put it in here, paste it in, when we will subtract this value from it, and equal. So 65,360. So, or so, sorry, 655,360. This right here is going to be the local distance. The 262 is what my neighbor is sending to me to get to the destination. You take those two and you combine them. So the 262, 144, and then the 655,360, those together equals 327,6800, which means that's going to be our feasible distance. So if I wanted to do any figuring out of how the network is broken down, I could look at this information and figure it out. Now, the other thing I was talking about earlier is if we were to look at the show IP protocols command, you'll see underneath here for EIGRP 100 that you'll see a total of 6K values. These are the metric weights that I was talking about. The metric weights, when you look at those, you see K1 is equal to 1, K2 is equal to 0, which means it's not being used in the calculation. K3 is 1, being used in the calculation. K4, 5, and 6 are not being used in the calculation. So I don't care about the load, reliability, or MTU, or the power. Don't care about any of those. All I care about is bandwidth and delay. Now I don't know why it's K1 and K3. That's just the way it is from my understanding, but that's basically how that comes into play. So that's just some of the details that you see. The other one, for example, that you see here is the rib scale. The rib scale is for in situations where you have regular the iOS routing table supports only 32-bit metrics. So in order to run dual on a 64-bit metric, which is what EIGRP named mode does, you have to basically take the total size and you have to scale it down, and the value here, this rib scale, is split in half, so it's 0 through 256. So if you want to make the rib scale, basically you're dividing with 128 effectively, and if you want to make this number lower, I believe you're going to have a higher output. So show IP route EIGRP, we can see that we're looking at 257, for example, and then some of these outputs right here. If we were to go to router EIGRP named mode, and then address family IPv4 autonomous system 100, and then underneath the topology table, topology and then base, if we were to use the, I believe it is the rib scale command, if it's underneath here, oh, it's metric, metric, and then, I'm sorry, it's not underneath that, it's underneath metric here, and then rib scale. If you were to use rib scale and say lower this down to say 1, and then do show IP route for EIGRP, you would see these numbers, those numbers look like they are potentially higher than what we saw previously. Yeah, so we had 90 and 15,872, and here we're now looking at 203, 16, 16. So by lowering the number, you drive up the cost. If I was to come in here and change this to be 255 and do this, the show IP route EIGRP, you would see those values come down from 90 or from down to 7967. So how you adjust the rib scaling by changing, you're basically changing how it's divided. So for example, if we look at the feasible distance calculation, so if we were looking at, let's look at, let me scroll up a little bit so it's easy, so we have the actual value in front of us. So we take this value right here. We take 32768 and we go ahead and clear the screen. If we take that and we divide this by 255, we come out with, the numbers don't work out exactly, but it's pretty close. So not too far off. So basically that's what's happening. You're dividing it by that value. And so the first one we came up with here was, let's see. This was with no modification, I believe, is what this comes into play. And then if we were to look at modifying it, I modified it to a value of 1. So if we were to take the 32, what was that value? Let me get back up to the top here. Let me just do here, let me jump out of global config. If I was to do the topology for this and then grab this value right here, 32768, here, paste this in, and then divide that by 1, it's not going to really come into play, but you're effectively, you're adjusting it so that it's not a division. It's not, the math doesn't work out exactly, but the idea is the lower the value you give in the metric rib scale, the lower the number is going to be. The higher the rib scale, the bigger the number is going to be. So you can adjust it based off of that. Never seen it done. Nobody uses it. Just basically the idea of how that would come into play. But wanted to give you an example of what that does. Now you might ask, why wide metrics? Why are they there? And the answer to that question is basically there was a limitation with classic metric calculation where you ran into an issue where up to a certain point you could only run certain speed links in EIGRP, and that was the best calculation EIGRP could do. That's fine, but it runs into problems when you get into much larger bandwidth options, 10 gig, 40 gig, 250 gig, so on and so forth. So you need a way to take the routing protocol and be able to scale with the link speeds. And so by changing the microseconds, or the delay computation from microseconds to picoseconds, you're actually taking that and scaling it so that it is able to calculate much more granularly. And instead of scaling via 10 to the 7th times 256, you're doing 10 to the 7th power times 65536. So you're going to a much larger calculation. The equation changes, so that also increases the speeds at which you can run at. So instead of being 1 gigabit, you could run at multiple terabits per second. I don't remember the exact numbers off the top of my head, but it's pretty big. The cool thing about it is this will allow you to scale your network. So if you have 10 gig and 40 gig and 100 gig, you can use EIGRP in those environments and do quite well. So that's basically where that comes into play. So with that being said, we've taken a look at how to modify the metrics with the rib scale. I'm not going to really play around too much with the modifications right now. That'll come into play when we get into like redistribution and stuff like that. But if we wanted to modify any of the values, we could. But for right now, I'm not going to mess with it until we get into some more advanced configs where we actually have to redistribute between multiple protocols. We're going to run into that scenario in multiple occasions later on, so I'll take a look at how to modify those values. So for example, just so you understand where I'm coming from, one of the things that I plan on doing is we actually have, let me go back to the pen tool and minimize this real quick. We have a couple of spokes that we're going to be using for doing tunneling. So just regular point-to-point GRE, crypto, VPNs, DMVPN, FlexVPN, all that type of stuff. And we have a couple of what could potentially be hub devices that we could take into effect. So what I'll be doing is I'll be taking those scenarios where we might be using OSPF over the tunnel, but then internally between these two guys we're running EIGRP, and I need to redistribute between two different protocols and then maybe influence traffic to go a particular destination. or a particular direction, that's one of the ways that you can do that, is you can play around with some of the K values and how they're calculated, and adjust basically how that would come into play. So just some things to keep in the back of your mind in terms of the operations and stuff like that. But that's really it in terms of the operations, but not much more than that from what I wanted to cover. I went a little deeper than I wanted to with this video, but that's okay. We're going to talk about that in more as we get further along down the road. But that's pretty much it where we are at. I want to thank you guys for stopping by and hanging out with me in this video, and we will catch you in the next video. Until next time, guys, thanks so much for stopping by, and I'll catch all of you next time.